Thank you. So welcome everyone. Thank you so much for joining today's CSML seminar talk. We have the great pleasure of having David Duvenaud here, who will talk about latent stochastic differential equations. David is an assistant professor in computer science at the University of Toronto. His research focuses on continuous time models, latent variable models, and deep learning. His postdoc was done at Harvard University and his PhD at the University of Cambridge. He also co-founded Invenia Labs, an energy forecasting company, and is a co-author of multiple very popular papers, such as convolutional networks on graphs for learning molecular fingerprints, automatic chemical design using a data-driven continuous representation of molecules, and most recently, neural ordinary differential equations. And today he will talk about how to do gradient-based stochastic variational inference in stochastic differential equations. And I'm thrilled to have him here today. So please welcome David.
Thank you very much. I'm thrilled to be here. And yeah, you mentioned neural ODEs, and I couldn't bear to name this model class neural SDEs because I felt like it was so corny that we chose that name for the first one. And these are latent in an important sense. One thing I also want to say is that, there is a lot of awesome work going on, like in the UK and everywhere, on doing inference in SDEs with other approaches. And I'm going to briefly mention those, but I apologize in advance to all the people in the related groups that I've talked to that I don't have time to explain more than one family of methods today. Okay, so just to let you guys know what you're in for, so you can leave now if it doesn't look appealing. I'm going to talk to you about a sort of a newish model class for continuous time generative models. And obviously, I'm not the person who thought of putting neural networks in SDEs. But the idea is, yeah, we're going to be able to parameterize the dynamics and likelihoods of some latent SDE model in a scalable way. And we're going to use stochastic variational inference to fit it. And so, like Maxime Rodzinski, for instance, sort of wrote down this model class and characterized it a couple of years ago. Our contribution was to generalize the adjunct sensitivity method for SDEs, which astoundingly hadn't been done. And you should be skeptical of that. And we have some evidence to back that up. But now we can bring this sort of constant cost memory training and adaptive solvers to the SDE setting as well. And something that's very new that is sort of hot off the press and we just submitted to ICML is that we managed to also develop an asymptotically zero variance gradient estimator for this setting. So yeah, I really like that one. So this talk is going to be because I think there's a few people here who are familiar with Gaussian processes or maybe like neural processes, stuff like that. I want to spend a little bit of time just talking about this is a new model class that has different pros and cons, and just give you a feel of like what I think this new sort of area will let us do that the previous ones didn't. And I say this as someone who did his whole PhD on Gaussian processes and was chafing at their limitations. So these have a different set of limitations, but also some new freedoms. I also want to say, please feel free to interrupt. And in fact, I think this is just going to be a more fun talk, even if those from, for instance, like who aren't familiar with SDEs ask questions. I didn't really know anything about SDEs a year or like 2 years ago. All right. So the main motivation for all this work was dealing with irregularly sampled time series. And, as a professor, people constantly come to me with their applied problems that they want help with, and I want to help. And often they have the data sets. So this is, for instance, medical data. This is the measurements made on a single patient over 48 hours in an intensive care unit. And so different doctors and nurses are coming and taking his blood pressure or his temperature or different blood readings. And so if we mark down the different types of readings at different times, we realize that this is not going to fit into like a recurrent neural network very nicely, or like a hidden Markov model, or even like a deep Kalman filter. So this, and also like in business, right? Like when we think of like user traces on the internet, or really almost all the data we collect comes in this ad hoc way, except with the huge exception of like video, audio, and text, right? So, but I guess I'm trying to say there's this like dark matter of data that has this format that we don't really talk about in machine learning because it's just really awkward to handle. And the people that I was working with were just going to bin it and say, okay, we'll average all the observations every hour. And I feel like in the future, there's going to be some sort of Hippocratic oath that statisticians take that says you shouldn't, like, whatever you do, don't just do a whole bunch of smoothing and imputation before you show it to the model. It's the model's job to decide what's data is worthwhile and what's not. Okay, so if we want to deal with data that comes in continuous time, I would say there's only a few different approaches that leaves us. And one sort of classic one that we're going to talk about today is differential equations. And just so that we're on the same page notationally, the idea is that we're going to assume that there's some hidden state of our system, Z, which is a vector maybe, and it's like the concentrations of chemicals in the reaction or the position and velocity of the planets or whatever. And then the change of that state through time is described by some function f, and that could be a neural network that depends on the current state and maybe time, right? And so what we usually end up doing to make predictions in these models is we say, okay, if I know the state at Z at time 0, then by integrating these dynamics along this gradient path, I can extrapolate to the future state whenever I want, or I can run backwards in time. And then the problem is that this integral has no closed form for any complicated f. So we're going to have to talk about different integration schemes. And like the simplest one and the oldest one is Euler's approximation, which just says, start at the current state and take a step in the direction of the gradient. And then from there, take another step in the direction of the gradient. This is a very poor solver in that it has quickly growing error. And then also it's not an adaptive solver. It doesn't try to monitor how much error it's accruing. So I'm not going to talk about this entire field of differential equation solvers, but suffice it to say, there have been 100 years of amazing algorithms that let us adaptively evaluate this gradient field wherever the algorithm thinks it's necessary to make an accurate extrapolation. So I want to say a lot of the earlier work on SDEs, I would say its main limitation is that it says, okay, step 1, discretize time, and then we'll use some sort of like Euler approximation. And that's fine, but it means that your model can't sort of zoom in and zoom out in resolution very easily. And in general, this thing is going to require many, many steps to to get a good approximation. So everything I'm doing in this talk is going to say numerical evaluation of differential equations is something that I'm going to delegate to the experts. And so I'm never going to take an Euler approximation for the rest of the talk. And we're always going to deal with the continuous time equations, and then in a form that we can send them off to a solver. Okay. So now I was saying we have this problem of continuous time data. How can we use these ODEs to address that? Well, the simplest thing, and actually you should always start with this because it's very simple and fast, is we could take a standard recurrent neural network, and you can apply these to irregularly sampled time by just having the hidden units update whenever we see a new observation. And now the funny thing about this is that this H, you could say, represents a belief state of the model about the system, and it doesn't update between observations. So a step towards a better model would be, let's say, keep the RNN updates when we see a new observation, because that should update our beliefs instantaneously, but allow our beliefs to change continuously through time, where there's some learned ODE that's telling us how our beliefs change as a function of time and the current state. And a simple example of this would be, let's say here I call my friend and I say, I'll meet you at the bus stop, or here, and then here I go to the bus stop and they're not there. And now I'm just waiting and they're not showing up. And my relative beliefs about what's going on with my friend are changing. And it's like, oh, he's just a little late. Oh no, maybe he's been hurt. Oh, until he does arrive, and then boom, I update my beliefs instantaneously. So the problem so again, this is like actually a pretty decent baseline. The problem with this model class is that it's not a coherent latent variable model, in that this H is just a big soup of all the information that I've conditioned on in my whole life. And it's hard for us to reason about it and use it as part of a larger probabilistic modeling framework. So a much sort of nicer model class for a number of reasons is latent variable models. And in a time series, they have this look where we have this state Z, which we never observe, but we do observe some noisy observations of it. And, the original Kalman filters had this form where this Z is the sort of state of a missile that's flying, and these are noisy radar returns. And if we assume that the transitions are all linear and the emissions are all Gaussian, we can in closed form, do missile tracking in like 8 bits of memory or whatever. And then the sort of newer, fancier version of that I really love is deep Markov models or deep Kalman filters, where we say from Rahul Krishnan and Shalit and Sontag that say, oh, let's just stick a neural network for this transition dynamics, right? It's 2015, you could still get a paper by just putting neural networks somewhere. Well, they didn't just do that. They also showed how to do variational inference. And we can also have arbitrary emission distributions or likelihoods. So for instance, this could be an image model, or even more radically, this could be like a text model. So this could be a doctor's note or something. And as long as the dependence of this likelihood on the latent state is differentiable, this whole thing can be trained end to end with gradients. And then the only awkward part is that since we never observe the Zs, and we can't really afford to make point estimates of them because then we would overfit, we have to integrate over the Zs. So we have to do approximate inference, for instance, by, in the old days, Markov chain Monte Carlo. Now they say, well, let's have a recognition network that looks at the data and estimates an approximate posterior over Z. So I'm afraid I don't have time to cover variational autoencoders, but that's what the framework is that we're going to be using for all the inference today. Okay, so the ODE version of this hidden Markov model is to say, it's something like this. It says there's an initial unknown state, and the state evolves according to an ODE. And now whenever we happen to see data, we know that, well, by assumption, that data only depends on the current state, right? So these are the doctor's notes or whatever, and they can come at any interval. And we can evaluate the likelihoods by just, again, doing an ODE solve to go forward in time until we get to the time we need to make a query, and then evaluating some likelihood. So this is all very abstract. As a simple toy example, we can show here is just in one dimension, if our data, or X happens to be one dimensional with a Gaussian likelihood. Here's some data that's sampled irregularly through time. Here's a few different data sets. We can fit this by that last model I just said, all together jointly at once. So the parameters we have to learn are the likelihood, like the parameters of the Gaussian, and the dynamics function f. So that's what this arrow plot here is showing, is what is the dynamics function in the latent space of this system. So here we're going to jointly train everything with gradient descent. And yeah, we see the dynamics. This is only a 2-dimensional slice of a 4-dimensional function, but they form some sort of swirls. And now the trajectories that our model guesses match the data, even though we only had this sort of irregularly sampled data with these huge holes in them. No problem. Okay, so that's the vanilla model that we're gonna start from. Any questions so far? Yeah, I mean, I think usually at this point, there's a few people who ask about identification or something like that. And I'll say, yeah, well, in general, there's a whole bunch of invariances here that we can't necessarily break symmetries, but that's sort of true of almost any latent variable model. Although of course, Apo Hyvarinen has some great work on this lately. But again, this is just a variational autoencoder. I'm only drawing the decoder here. Just to make inference fast, we're also training a neural network that looks at the data and outputs an approximate posterior over the initial state. Okay, and when we applied this to that hospital data, and it works better than the previous things because it generalizes them for the most part. There's also a variant that I don't have time to talk about that lets you condition on the time that the observations were made, which helps a little bit. And the idea is that, just knowing that an observation was made can sometimes be very informative. For instance, if I showed you 2 different medical charts, but I erased all the actual measurements and just showed you the timestamps of when measurements were made, basically the one that has like yearly checkups, you think that person's healthy, and the one that's like yearly checkups and then suddenly a whole bunch of tests, probably something's going on without even seeing any actual data except for timestamps. So that requires a Poisson process likelihood, but that's just another ODE, so it's really easy to fit into this framework. Okay.
Sorry, can I ask a quick question?
Yes, please.
So the RNN VAE on that slide, would that be the Euler integration counterpart of the ODE version that you just talked about?
Yeah, I think you could say that, except that the way they set up the deep Markov model is this transition isn't linear, but it is similar in spirit in that we have to discretize time first before we do our integration. And it's not Euler integration, but it is a similar in spirit setup. And so I think that's a great model class if your data does come at regular intervals. Like there's really, I think, not much advantage to moving to continuous time if all the data you're ever going to see comes at regular intervals.
Yeah, okay.
I want to mention there's a few people. Thanks. There's a few people who disagree with me and they say, oh, I'm going to fit continuous time models to video, and then they can do cool things like interpolate between frames and stuff. And I'm not like, I think that's a cool idea. I guess I'm trying to say it's usually not worth the cost if you're, but I might be wrong about that. Anyway. Okay, so now I've set up that we want to build continuous time models. But I think this latent ODE is not quite satisfying. It was, I think, certainly worthwhile, but the crazy thing about it is that it has these deterministic dynamics. And so what that means is that according to this model, everything that ever happens to this person or system or business or whatever is determined sort of at birth, at time 0, by whatever's in this random node. And that's the only place where things can vary between people. So if someone gets hit by a car when they're 20, that has to be somehow foretold by this model by some aspect of their state at time 0. But of course, in reality, we know that there's all sorts of weird, random interventions happening to people or systems that we don't get to observe. If we do observe them, then we can say like, oh, there's, these little updates to the state, and that's a simple extension. But the problem is, how do we integrate all over all these tiny sort of slings and arrows that affect our systems? So this works fine on this sort of ICU data where there's really, a fixed time horizon and there's only so much stuff that's going to happen in 48 hours. But we want a model that can handle short or long time sequences and just roll with the punches. So this brings us back to stochastic transition dynamics. The one way in which we didn't generalize the deep Markov model was that our transitions are deterministic and theirs are stochastic. And this stochastic transition dynamics is a great place to say, oh yeah, and maybe something else happened to my system that I didn't get to observe. So yeah, if we look, we can also, I guess I said I wasn't going to look at Euler updates, but if we phrase this kind of arrow as my new state is my old state plus some nonlinear thing plus some noise, that starts to look a lot kind of like a Euler-Majorana step, like the SDE version of Euler. And one cool thing I want to mention is that, or one cool thing about these generative models is that they can handle missing data automatically. So for those familiar with DAGs, the idea is that these observations are all leaf nodes. Basically, we know that if there was some X we didn't see, it's likely it has to integrate to 1. So we can just remove it from the model and we get the exact same joint distribution over everyone else. So if we wanted to imagine chopping up time even more finely than we did, even in this deep Markov model, that's actually okay, because it's okay for us to have missing observations in all the intermediate time points. The only cost is of doing all these unnecessarily fine steps. Yeah, generative models are just such a natural motif for missing data. That one way to think about what we should do next is to say, I could turn this deep Markov model into a continuous time model by just chopping up all these transitions into like epsilon amount of time and integrating over all the observations I don't see, which I can do for free. Okay, so anyway, there's a few different motivations that all lead us to the same model class, which now I will like reveal. It's it's like a 70-year-old model class, which is stochastic differential equations, which I think I found the whole, I found this whole area intimidating when I first started learning about it. And I think it's a mishmash actually of a few ideas that don't need to be combined. But the basic idea is that we want to have a differential equation plus some noise. So this is like informally, we just want to add some noise at every time step. And then formally, the way we end up writing this is, okay, we have our ODE. So we need to bring dt up here. Now we have an ODE part. And now we're going to add, we call that the drift. And then we have this noise part, the diffusion. And this looks, I don't know, I found this intimidating because I don't have a very strong math background, but the basic idea is that this sigma is just a function like f that says how much noise should I have? How much should I scale the noise at every step? And this dbt, that's just, you can think of this as independent Gaussian noise. And we just happen to write it as the difference in integrated Brownian noise. And that's just so that we can take limits sensibly to like 0 time steps. So this kind of looks like the reparameterization trick of a Gaussian, right? Where we have the mean and the standard deviation times a normal, like a unit normal, a standard normal Gaussian. Okay, and then the cool thing about this is that once I write down these two functions and I specify an initial state or an initial distribution at like some time 0, I've implicitly defined an entire distribution over functions. So this is kind of like, you know, Gaussian processes. It's just a way of writing down distributions over functions is how I think of it. And on this plot here, I just want to give you a little bit of a concrete idea. This drift function here is being shown by these little gray arrows. And so the idea is that when I want to sample from this distribution over functions, I start at time 0, sample a point, I keep adding noise and then also moving according to whatever the gray arrows tell me. And then I can get all sorts of complicated distributions over functions by the interplay between the diffusion that's spreading things out and the diffusion or the drift that might be squishing things or spreading things. So here, for instance, I actually start with a very wide distribution, but the drift kind of pushes things together. So I can end up with arbitrarily tight marginals if I want. This looks like a very simple and limited class of models, but it's actually sort of arbitrarily flexible in some important senses. Okay, and you know, SDs are cool. I was saying that the thing that's missing from our model is that we think that there's lots of tiny little interactions of, you know, diseases that someone caught, or they stub their toe, or, you know, customer buys something. And the original Brownian motion was actually from this guy Brown looking at these dead pollen particles and wondering why they're still moving. And of course, people realized, or Einstein, his first big contribution was to say, oh, it's because all the little water molecules unseen are pushing it around. Also, allele frequencies in a gene pool, anytime an animal dies or has a baby, its genes frequencies go up or down. And or in a market, anytime someone learns something or makes a trade, that makes prices go up or down a little bit. The crazy thing that I think is not intuitive is that these interactions don't need to be Gaussian. As long as the central limit theorem kicks in, like as long as they have any sort of well-behaved variance, then you can describe these kind of like millions of tiny interactions asymptotically arbitrarily well by this mean plus standard deviation times a Gaussian change instantaneously. Yeah. So people sometimes say, well, what if this seems limiting? Why are you using a Gaussian here? And I'm saying it's fully general. Well, in sort of the important sense that you would hope for. Okay, so I'm just a deep learning hack, so I'll say let's stick a neural network in F and sigma and fit its data. And then it turns out that that's hard, and that there's a bunch of people that sort of said let's do this, and I'd say, did it in ways that were missing an important part, either for scalability or for consistency. So the next part of the talk, I'm just going to talk about the missing pieces for why people didn't fit neural SDEs until 2019. And it's kind of delightful. There was like a $20 bill laying on the ground that we picked up. So, so when we, question?
Yeah, so you mentioned that you can kind of fit in some any random interventions between the timeframes, right? So could you share some intuition on where do you imagine them getting fit? Like, is it the drift part, or do you imagine like diffusion getting affected by interventions?
Yeah, so the diffusion is what is modeling the interventions. So the idea is that these are, okay, so the model assumption we're making is that there's infinitely many, infinitely small interventions being made to our system. So this noise, that's the random interventions. So I will say the whole big thing that this whole approach is missing is like giant instantaneous interventions. And so like jump processes or levy processes, I think would be a good fit for that. And I kind of think that that would be a nice direction to go next. But I guess I'll say, you know, you can, we're most of the way there if we can say there's a lot of small interventions.
And do you imagine like giant interventions being distributed into small ones and then they giving a cumulative effect nonetheless?
Yeah, that's the hope. It's like the way it's someone getting hit by a car would be modeled in this system by like, oh, this guy has a series of very bad moments in a row. It's not a perfect fit. I totally agree. And I also want to say, you know, there's some nice, I forget the name of the theorem, but it says that any stochastic process can be modeled as an SDE like this plus a jump process. So if we did add jump processes, which I think would be like not technically terrible to do, then we would have a sort of like universal model class in some sense.
Thank you.
Oh, thank you. It's so much more fun to give a talk when people ask questions. Okay. Right, so the first part is how do we even compute gradients of sample paths from SDEs? And you know, in the neural ODEs paper, we basically said, oh, this has already been figured out 50 years ago. How do we compute the gradient of some scalar loss of the output of some ODE initial value problem? And the main thing I'll say is that, you know, probably for small systems, Backprop through the solver, totally fine, is very stable. You can't really go wrong. And the thing is just if you have very large systems you want to integrate over long time periods, Backprop requires you to store all the intermediate states, which is too memory expensive. And then of course there's checkpointing approaches and like there's a sort of time and memory trade-off. But we're going to say that there's a way to almost entirely avoid that whole trade-off, and at least in ODEs and then now in SDEs. So, you know, there's a bunch of, everyone derives this using this like functional Lagrangian approach, but I think that's confusing. I like to think of it as, here's the Backprop equations for a ResNet. Backprop in a ResNet is just, we start at the last layer, we update by the Jacobian of every layer, and then we sum over all the layers. And sort of rewriting what the numerics people did, you know, in this form, it's again saying, okay, if we want to integrate an ODE, or do Backprop in an ODE, we start at the last layer, instantaneously update by the Jacobian of every layer in the neural network, and then sum over all the layers. And these Jacobians are multiplied by vectors. Jacobian vector products are cheap. You never have to instantiate a Jacobian if you're going to multiply it by a vector. So all of these operations have the same time cost as evaluating F. So this is the machinery that gives you Backprop, like in PyTorch, can just be reused to do Backprop in an ODE. You just have to make these vector Jacobian products be the dynamics of an ODE. Anyway, so the upshot is that the function that gives me all the gradients that I need is just another call to an ODE solver. And that can be a black box ODE solver. I don't have to know how it's doing its business internally. And the real win is that we don't have to store all the intermediate states to do this Backprop. So the idea is that in an ODE, it's sort of, if I can run it, well, I can run it forward to solve the initial value problem and then starting at that final point, I can just run the dynamics backwards to reconstruct this state arbitrarily well. And when I was saying this, the numerics people, I think rightly said, well, whoa, like, maybe, but if this system is like stiff or, convergent in the forward pass, it's going to be hard to solve in the reverse pass. And so I guess I'll say, yes, there's, this thing can definitely fail. It can be arbitrarily hard to run backwards. And in that case, we will have to do one of these like checkpointing schemes where we, solve forwards and like, remember the state every so often. But it turns out we're lucky that in the sort of the like over-parameterized high-dimensional regime, at least in practice, we don't seem to see these hard to reverse dynamics, or at least if we do, maybe the system gets really bad gradients and goes to another part of the state space. But we sort of have enough slack to play with in this like over-parameterized neural network regime, much more than in the standard like physics regime where everything tends to be very stiff and like very tightly coupled. Anyway, the nice thing is that it doesn't really silently fail, because if I go forwards in time and then I reconstruct backwards, I can just check whether I made it back to my initial starting point. And usually it still can silently fail in principle, but usually if something went wrong, you won't end up at the same starting point. Anyway, and one cool thing about ODEs is that to run one backwards, you can still solve a forward ODE by just sticking some negative signs in front of everything. Okay, so there's this algorithm that is like the adjunct sensitivity method that I mentioned before, which just says, build this augmented system that has an extra set of Jacobians times vectors, send that to a big ODE solver, right? And this is old, this is standard stuff. Why? Okay, I wanted to write the neural SDE paper, so why can't I just run this adjoint sensitivity method on these ODEs with noise? And it's hard, and you shouldn't take my word for it, but you can ask Maxime Roginski. He wrote a whole paper where they worked out all the gradients for SDEs, or rather, like they've sort of been around, but they kind of put them all in one place and sort of set up the problem, especially with respect to variational inference. And then they said, oh, it's actually not obvious how to construct like adjoint method for SDEs, right? And these are like serious measure theory probabilist people who are, know much more math than I. Patrick Krieger and a bunch of other people have been approaching this from a different path, a different direction, which is rough path theory, which basically breaks SDEs into non-differentiable functions and distributions over functions. And I think that's actually a really good refactoring of SDEs. And that approach really treats things as ODEs with noise, and it has a bunch of different pros and cons technically. Maybe we can talk about that later. Anyway, so me being a sloppy mathematician said, okay, well, we have this extra term in our SDEs, so why don't we just slap some more negative signs on there? Like, okay, there's like Ito integrals and Sturtanovich integrals, but if you know the definition of those, it's pretty clear that you want the Sturtanovich one because that's the one that physicists use because it's time reversible. And I coded this up and I was able to reconstruct my trajectories running forwards and backwards. And I was like, this has to be right. Like, what else could it be? And this very careful undergrad that I work with, Zhuochen Li, and this probabilist at U of T, Leonard Wang, they were like, what does that even mean? Run an SDE backwards. You have this filtration of like infinitely many random variables that are conditioning on each other, and you get forwards, and then you're going to also condition on themselves from the future backwards in time. Like, this is a weird divide by zero kind of thing. What does that even mean? And then I was like, it works, right? The algorithm works. And they, with very little, like, I wasn't even really able to help here. They had a strong enough background in probability theory that they could actually prove that this is correct. And that there exists another SDE that you can run backwards in time that reconstructs the strong solution. So what I mean is, for a fixed Brownian motion, like if I fix the randomness and I integrate forward in time, then I can construct this reverse SDE and it will reconstruct the same path if I integrate that thing like backwards in time. And it turns out that one of the like original SDE guys had been sort of talking about similar things informally, and so we built on his work and just kind of, well, made it into like a complete package. Okay, and so then the remaining part is I said, okay, how do we store the noise? We know how to store a finite number of random variables, but how do we sample an entire sample path from a Brownian motion so that we can integrate our SDE path? And it's kind of cool because, the reparameterization trick was a big deal in 2013 when the two VAE papers introduced it or rediscovered it. But SDE people already set up their whole formalism to do that with like an infinite dimensional reparameterization trick, right? They already, where is that? Yeah, they already took all the noise in their model and made it into one Gaussian process with no parameters. Anyway, so if we can just somehow sample from that Gaussian process, we're done. And then, so the last technical contribution we made was to say, okay, there exists, due to Terry Lyons, this Brownian tree where you can sample any, if you ask, okay, I want to know what is a sample from this Brownian motion at this time, you can keep sampling the edges of an interval that contains the point that you care about and just sort of zoom in arbitrarily closely. And each of these conditional distributions is just a Brownian bridge. And all we did is we said, oh, if you keep track of your random seeds carefully and make the random seed a function of which leaf on the tree that you're at, you don't even need to ever store, you can reconstruct any of the intermediate samples that you make at any leaf. So we can just, if you ask me for different values at different time points, I can always just go back to the top of the tree and follow the part that I need and reconstruct all the samples deterministically by keeping track of the random seeds in a nicer way. So this is really nice because now I can sample arbitrarily accurately from this, Brownian motion sample in constant memory. And I have this logarithmic time cost where it's like, how many times do you have to bisect to get like close enough in time to the point you're interested in, right? And so if I'm using like float 64, this is like this is like a constant is upper bounded by 64. Okay, so so then the big reveal is there is an adjoint sensitivity method for ODEs. There now exists an adjoint sensitivity method for SDEs, which is just you copy the thing that you did for the drift and do it for the diffusion too. It's sort of just, again, what you would guess. It's like just by pattern matching. It's very simple. So it's a lot of math to get to the thing that the person would just guess is the right answer. Okay, so now we have this, I would say, like tractable way to fit SDEs with gradients. And so to be specific, like for instance, Chris Rukakis, like the Julia people are saying, look, just do forward mode differentiation. It's fine if you only have 100 parameters, and that's true. And that also has constant memory costs, but your time cost is linear in the number of parameters you have, which is, I think, unacceptable if you want to have a neural network anywhere. Then Backprop 3 solver. This is also known as discretize then optimize in the like numerics community. That's also very stable and fast, but it just has high memory costs. So linear in the number of steps that we take. And then our setup has constant memory costs, and the time is just L log L. And in practice, this log L is actually not that bad. Okay, so
sorry, quick question. L was the number of function evaluation. So what was that again?
L is the number of steps in my, like time steps in my integration. Sorry, I didn't say what that was.
Right, thanks.
Yeah. Okay, so, and then the last part is I want to say, sure, SDEs are fine, but we actually can't just fit them. We can't just fit them by maximum likelihood, because then we will turn off the noise part. Like if you want to fit some observations and then if part of your model can add noise, maximum likelihood will just turn off the noise always. So we have to do maximum marginal likelihood, where we say, okay, we have a prior over functions. So this is the thing I've been talking about the whole time. This is just like the latent ODE model, except now this is an SDE solver. Then we have to have an approximate posterior over our functions. And so we can quickly estimate that with some recognition network that, again, it looks at all the data and outputs the parameters of an SDE. So this is probably the last sort of hard idea in this talk, is that we're going to write down a prior over latent functions with an SDE. And then it turns out like, okay, now we have to do approximate inference. Maybe we'll like use a Gaussian to fit it. No, we can use another SDE to parameterize the approximate posterior. And so what this ends up being is an infinite dimensional VAE, where, well here, okay, this W, that's the Brownian motion. So we can factor out our randomness. And so just like in a VAE, we have like a latent Z that's Gaussian in the prior and non-Gaussian in the approximate posterior. Now we have like an infinite dimensional Z that, well, it's an SDE in the prior, and it's also an SDE in the, it's a different SDE in the true posterior and the approximate posterior. So I don't want to be too catty, but there was a couple of papers that said, oh yeah, we'll have an infinite dimensional VAE by just like sticking a Gaussian process in there. But I don't think that their losses quite made sense. Here, I think everything fits together, and like the finite dimensional version of this thing is also sensible. All right. So, right. I'll just I'll skip to the slide where I put it together. So the idea is that our prior over functions, we have some drift function and some diffusion function. Okay, and so maybe this is like an OU prior, or some usually we'll choose like a simple SDE for the prior. And then we'll say, to do inference in this model, we'll parameterize an approximate posterior with a different drift function. And his job is to like steer the sample paths to the region of high posterior probability. One funny caveat is that the diffusion function of the approximate posterior has to be the same as that of the prior. And that's the only way, in like, if you don't do that, then the KL divergence between the prior and the approximate posterior is infinite. And you might think, oh, this is a really serious limitation, but I don't want them to be like equally noisy, but it's actually not a limitation. And I'll talk about that a little bit more. So anyway, so inference in this model looks like write down a prior, write down a likelihood, and then condition on some data. And now we're going to tune our drift function of our approximate posterior to make it match the true posterior. And so it turns out, and this is not to us, this is Gershonov's theorem. When you write down the elbow, the standard variational evidence lower bound, it ends up looking like another SDE, or like random ODE, another integral across time of this squared error between the prior and the posterior drifts. Yeah, so basically at every single, well, the way to estimate this is we sample a path over our approximate posterior, and we see how much does our approximate posterior drift look different from the prior drift, scaled by the diffusion. And so this just looks like the KL between two Gaussians. So again, just like a SDE, it's like fully general for it to just be sort of marginally Gaussian noise. Then the elbow looks again like, oh, how well these two little Gaussians match locally along all my sample paths. Okay, I don't want to spend too much time on algorithms. Now the payoff, this is what fitting these models looks like to data. So here, here the crosses are actual data. Here I'm showing you the blue shaded area, and the purple sample paths are all from the prior. Right, so the prior is an OU process which says send the density towards the center. Now, when I optimize that elbow using all the machinery I showed you before, we end up with another SDE that characterizes the approximate posterior, and it does what you think. It's like, okay, the drift learns to send the sample paths to be near the data, but because it's variational inference, it's Bayesian, it does the right thing, which is that it maintains uncertainty where there is no data, right? So this is, this is an OU prior. So the prior is actually a Gaussian process, but we're using a Laplace likelihood. So the true posterior is not a Gaussian process. the approximate posterior, but the nice thing is our approximate posterior doesn't have to be a Gaussian process either. Okay, so this is probably a good place to stop for questions because this is like showing these models in action. And this is just one dimensional. Like this all can work with like a 1,000-dimensional state. I just can only show you 1 or 2 dimensions at a time. Yeah, so I'm saying this is this new model class that we can now explore. There's PyTorch code available. You can use any likelihoods you want, and this scales, well, yeah, this scales to like millions of parameters. It's the standard like scaling regime of any deep learning method. Okay, and I mentioned that I would sort of talk about pros and cons of this model class. So yeah, so in GPs, we have these like mean and kernel functions that we specify, and that gives us a prior over functions. Here we have the drift and diffusion functions, same sort of thing. However, this is what killed me when I was a PhD student is if I take a function that's drawn from a GP and I like transform it, like I say, oh, I'll take the exp of that function, then I don't have a GP anymore. And so I can't really use my machinery. But as SDEs, just by Ito's lemma, are like, you can just write down, if I know the drift and diffusion for this function, I can write down the drift and diffusion function for like the exp of that function or any, you know, differentiable nice transform. So it's like it's closed under more sort of transformations that we normally want to do than GPs. However, you know, GPs can work on like, you know, spatial data or as many input dimensions as you want, whereas these Markov SDEs really, they only make sense or they're only efficient in like 1 time dimension. Although the state again can be like 1,000 or 1,000,000 dimensional. Cool. And then just to show that this actually kind of works on higher dimensional data, here's us fitting, this was like a pretty toy data set, but like, so we have 50-dimensional time series mocap data. So like the position of all these different sort of joints on a person. We used a 6-dimensional latent space. This is just because it was like when we just were coding everything up in PyTorch and it was very slow. This was like a 1.5 years ago. So this is fitting 11,000 parameters. So since then, Zhuai-Chen Li and Patrick Krieger have been iterating on this PyTorch code base, and it's like much faster and more scalable, but we haven't really revisited it to make any nice demos yet. But of course, this generalizes latent ODEs, so it kind of has to do a little better at least. And oh yeah, okay. And then the last thing, the very new thing I want to show you guys is that we had this paper from 2017 that says the one problem with stochastic variational inference is that you have noise in your gradients from this random sampling your Zs from your approximate posterior. And so you never settle down, right? Like the nice thing about deep learning for regression is that eventually all the gradient norms go to 0, but that doesn't happen for stochastic variational inference. However, we showed that, I mean, this is kind of a well-known identity, like David Bly talks about it, but there's like a term that you can remove from the gradient estimator that has zero expectation. And if you do remove it, as your true posterior as your approximate posterior approaches the true posterior, your gradient variance shrinks. So when you get to the optimum, you stay there without having to adapt your learning rate. And this was kind of just a curiosity though, because normally we'd still just use like a Gaussian or some simple form for our approximate posteriors. So the cool thing about this SDEs is that they have these arbitrarily rich approximate posteriors that, like, if you made your neural networks big enough, would actually contain the true posterior. So they can have like multimodal, crazy distributions, whatever you want. So that's a really good. So we just like did the math to extend this this variance reduction trick to the stochastic differential equation setting, and now we have a gradient estimator whose variance goes arbitrarily low as you get close to this true posterior. Okay, so yeah, the takeaway is we have this new model class, and then I actually messed up my time a little bit, but the things I'd like help with are like, well, I think we can have these sort of like multi-scale SDEs that like let us skip over irrelevant details, kind of like climate series or climate models that have like, you know, the coarse grain variables and then the fine grain variables. We need to add jump processes, extend this to PDEs. And then just very quickly, one thing that we did with this setting was fit infinitely deep Bayesian neural networks, where we say, if a ResNet is like an ODE in the limit, a Bayesian ResNet is like an SDE in the limit, and then it has like infinitely many parameters. And so its activations end up, following these SDEs. We can use this machinery that we just built. And this is just like a for fun demo to say, now we have a Bayesian neural network where we don't have to have a Gaussian approximate posterior or try to build some normalizing flow and worry about the trade-off between number of parameters and having any cubic blowups. We just have this like SDE solver that adapts the complexity in a more automatic way. Okay, so sorry, I took too much time. These are just like for fun, like thinking about the future and ways that we can like take advantage of this rich model class. We also have to try to somehow learn to make the dynamics easy to solve. Like we did this for ODEs at this last NIPS. Anyway, I want to make sure there's time for questions. So I do have to say though, that Zhuotian Li is really the guy who worked out most of the math and coded up the first versions of all this. He's the sort of the adult in the room mathematically. And Winnie's the one who got all the Bayesian neural networks to work. And I mentioned Leonard was our probabilist friend who helped us actually prove things in a way that we believed were actually proved. And Ricky and Yulia are the ones who got all the latent ODE stuff to work. So thank you very much.
Thank you so much for this great talk. I will now stop the recording.